This is an RNZ podcast.
Kia ora and a very warm welcome to Elemental, a podcast from RNZ. I'm Alison Ballance.
And I'm Allan Blackman from the Auckland University of Technology. And since this is episode 32, believe it or not, that means that we have in fact completed 1/3 of our journey through the periodic table, marking 150 years since it was first published.
Now, I bet many of you are wearing some of today's element. I certainly have a very small bit on one of my fingers.
And that's because, of course, we are up to gold, the most noble of noble metals.
Which begs the question, what is a noble metal? I remember doing noble gases. They were quite indolent.
Indeed, noble gases, so named because they are relatively unreactive, and the same with noble metals. That terminology coming also from the same idea, and gold is a relatively unreactive element. Now, noble, the term noble metal does in fact have slightly different meanings in different fields of studies or applications, but when you go to atomic physics, there is in fact a strict definition, and the noble metals there are defined as being only copper, silver and gold, because they're in the same group of the periodic table, and because of that they have completely filled d orbitals, or d subshells if you will. The name gold, where did that come from? Well, it comes from the Anglo-Saxon word gold.
Funny that.
I know. But the Anglo-Saxon word may, they're not sure, may have come from the word giolo or giolo. I'm not sure whether it's a hard G or a soft G. And that means yellow, apparently. So the vital statistics of this element, so we're talking atomic number 79 and the elemental symbol Au. And it's a group 11 transition metal.
Now, can I just stop you there? Au, this is one of those other ones that the chemical name seems to have no relationship to its common name. So why does it have Au as a symbol?
Okay, so we often find that those elements that were known to very early humanity, shall we say, generally have names that seem to have nothing to do with its symbol. And the reason for that is generally because their original names were Latin, and gold is no different in this respect. So the Latin aurum, A-U-R-U-M, and that means glow of sunrise. So that's where we get the chemical symbol Au from.
Oh, that's very poetic. Why is gold even gold when most other metals are grey or silver?
Oh, that is a very, very tough question. And so I'm going to say, in 2 words, relativistic effects. And
yes.
If you want to know any more about that, I suggest that you contact Professor Peter Schwertfeger at Massey University, and he will tell you all about that because he's a world expert on that sort of stuff. So I defer to him.
So having slid out of answering that one, what else are you going to tell me about gold then?
Okay, well, as I sort of alluded to before, gold has been known since ancient times, and it is one of the few metals on the periodic table that we do find in its native state. So we talked about copper, for example, a few episodes back. Gold is similar, as any of you who've been gold panning will know. So gold has been found in graves in ancient Iraq, or as it was known at the time, Ur, around about 3000 BCE. The Egyptians got into the gold business. They were mining gold by around about 2000 BCE. And the first gold coins were minted in ancient Turkey, a place called Lydia, under a fellow by the name of King Croesus. So we get an expression in English, as rich as Croesus, which you may have heard.
So that means we've been basically valuing gold. It was obviously valuable enough to want to bury with important people for 5,000 years.
Yep,
and
pretty much.
Why is it that we've always liked it so much? Is it because we not only like the colour, but that we've also found it easy to work with at room temperature? It's quite a simple metal to work with.
Yeah, indeed. Gold holds the records for being the most malleable metal and the most ductile metal. So any of you who've studied chemistry at school will know that 2 of the properties of metals indeed are that they are both malleable and ductile. So malleable means that it can be beaten out into a sheet. And you can take 1 gram of gold, which, because it's so dense, is around about the size of a grain of rice. And remarkably, you can beat that out into a sheet that's 1 square metre, which is quite astonishing. Rutherford used one of these very, very, very thin gold sheets in his famous gold foil experiment. And you can take around about 28 grams of gold, which is an ounce in old money, and you can draw that out, believe it or not, to make a wire that's 80 kilometres long.
Gracious, you can make a lot of jewellery from that.
Well, very, very, very thin wire. The other reason why we like gold, well, again, it's found in its native state, so that means that it's very, very unreactive. One might call it boring even, and the beauty of it is that it doesn't rust. It keeps that lovely gold metallic lustre on exposure to all of the worst that the world can throw at it. So pure gold itself really is pretty unreactive. However, one of the things that it will react with, and in fact it dissolves in this, is a thing called aqua regia. And again, I believe that's Latin for water of kings. And that is made up of 3 parts of hydrochloric acid and 1 part of nitric acid.
Now, I read a story about aqua regia, and it was to do with a couple of Nobel medals that were being hidden from the Germans during World War II. And I think the scientists ended up dissolving the medals in aqua regia, and then they just left the beaker sitting on the shelf in their deserted lab. No one gave it a second look. At the end of the war, they went back. The beaker was still there. They precipitated the gold back out, and the Nobel Committee had the medals recast.
An absolutely true story, that. Yes, yeah, it's a wonderful story. I do like that. And Nobel medals are really a big size. I remember when Allan Blackman, the New Zealand Nobel laureate, came to visit, and he actually handed his Nobel medal around the audience, and solid gold, and they're big suckers. So they're worth a bit.
I think the scientist who dissolved them out said it took quite a while. It doesn't happen very quickly.
Yes, indeed.
Now, people like gold so much they've actually put huge amounts of effort into trying to create it from cheaper elements, haven't they?
Well, yes. And I mean, this is an interesting historical fact, I guess, that chemistry as a science really is only about 300 or 400 years old. And prior to that came a thing called alchemy. And the whole guts of alchemy was that people wanted to turn base metals into gold through the use of a thing called the philosopher's stone, whatever that might have been. So many, many, many people spent many years trying to do this sort of stuff. Of course, they didn't think through the economics of the thing, because obviously if you could make gold from, I don't know, lead or tin or something like that, then obviously the price of gold is going to go through the floor if you can start making it at will. So one person, the Roman Emperor Diocletian, who was around from 285 to 300, he was so concerned about this economic impact, he seemed to be one of the few people who'd thought about it. He figured out that if somebody was successful in actually turning these base metals into gold, the economy would go haywire, and so he ordered the destruction of all alchemical texts, which I find quite funny. And even some great scientists were not immune to this. The great Isaac Newton, sadly, was an alchemist. And after literally thousands of years of alchemy, it died a death and nobody succeeded, although I'm sure there are still people around on the internet today who will swear by it.
Well, because we can't make gold from lead, it is really quite a valuable commodity. But really, why is it so valuable?
Well, it is valuable. Currently $61,000 a kilo. That's pretty valuable. Probably 2 things, I guess, give it the great value. Obviously, its rarity. So there's not really a heck of a lot of it on Earth. And its beauty, you know, that lovely gold lustre. It really is quite gorgeous. To give you some idea of its rarity, and this is an estimate, and this just blew me away when I read it, that all of the gold mined on Earth would fit into a cube that has sides 20 metres by 20 metres by 20 metres.
It would be a very heavy cube.
It would be an enormously heavy cube. But I think that's utterly astonishing. So really, there's not a hell of a lot of gold out there. But one place where there is a lot of gold, relatively speaking, I guess, is in seawater. So it's estimated again that there's over 10 million tonnes of gold in seawater.
Oh, let's go mine it.
You're not the first person to have that idea, Alison. Now, the trouble with this is that it's at a concentration of about 10 parts per trillion. So all you've got to be able to do is to concentrate the seawater and you can get gold out of it. And a very famous chemist by the name of Fritz Haber, he won the Nobel Prize for Chemistry in 1918. He was German. And he thought, oh, okay, we've just been hit with all of these war reparation payments. So if I can get all of this gold out of the sea, I'll be able to pay all this money to the English and the French for starting World War I. And needless to say, he failed.
Isn't real gold quite soft? I've heard of people biting it to determine if, is this really gold? And if you bite it, you can leave little teeth marks in it.
Yes, that's true. And pure gold itself is quite soft. And we measure the purity of gold in a thing called carats. And so 24 carat gold is said to be pure. Anything less than this, it's usually alloyed with something. So we talk about 18 carat or 12 carat or 9 carat gold. And obviously the lower the number, the more other elements are in there. Usually the elements it's alloyed with are silver or copper. And to harden it up a bit, you normally put in a touch of zinc as well.
That can end up making different coloured gold, can't it? I mean, I think there's white gold, red gold. I even read of blue gold.
Yes, but it's not real pure gold. There's only gold in my book. So when they talk about white gold, you know that it's absolutely not pure.
Now, I remember back in 2011, and I'm thinking this is a New Zealand connection to gold, there was quite a buzz in New Zealand science and in fashion circles about nano gold textiles, especially merino wool, and the nano gold particles made the wool a beautiful purple colour.
Yeah, indeed. And this is an area of chemistry that was sort of developed in the 1980s and is to do with these things called nanoparticles. And in particular, gold nanoparticles are of quite significant interest. So when we're talking about nanoparticles, we're talking about really, really, really tiny bits of gold, essentially. Bits of gold that have dimensions of a few nanometers or a few tens of nanometers. And what we find is that when we get down to that size, gold stops being a gold colour, and in fact it can be a whole host of different colours depending on the precise sizes of these gold nanoparticles. So when you go to about 10 nanometer nanoparticles, you get a lovely sort of red wine colour. You go out to 100 nanometer gold nanoparticles, you go from red to purple to blue, and you finish off as various sort of shades of grey. So this is quite remarkable stuff. If you want to know how this happens, it's localized surface plasmon resonance of these nanogold particles. And so these were used to bind to the wool through linkages to the sulfur atoms of amino acids in the keratin protein. And yeah, really, really interesting that. And I don't know really what's happened with that recently. I haven't heard a lot about it. So gold nanoparticles really revolutionized our understanding of gold. And so instead of, being very sort of non-reactive and always the same colour and everything, when you get down to the nanoscale, it starts getting very, very interesting.
Now, I've got another New Zealand story to lob in here, which was one I covered a few years ago on our Changing World My Science program, and it was with a geologist at the University of Otago in Dunedin. And he was an expert in gold, particularly alluvial gold in streams and rivers. And Dave Craw told me that there's a whole school of thought now that gold nuggets are formed basically from gold flakes. So the gold starts off as tiny little flakes of gold, and that somewhere along the way in these rivers, bacteria end up clumping all those flakes together to make little gold nuggets. And so it's got this whole bacterial biological process that makes the nuggets, which I thought was extraordinary.
Good grief. So bacteria can actually chow down on gold. I think that's very, very cool. I did not know that.
Now tell me something I don't know.
Well, as I said before, gold is very unreactive. It's hard to dissolve, and it's in fact insoluble in nitric acid, and pretty much all other metals are going to dissolve in nitric acid. Certainly silver will, and your base metals that you might mix gold with. So therefore, this is a test to see whether you've got pure gold or not. So you put it in nitric acid, see if any of it does in fact dissolve. If it does, then that means your stuff is not pure gold, and this gives rise to the term the acid test.
Huh. Well, I hope this podcast series is passing the acid test for all our listeners out there. You have been listening to Elemental, and you can find us as a podcast in all the usual places and online at rnz.co.nz/chemistry.
We're back next time with something rather less well known than gold, in fact very much less well known than gold, hafnium. But until then, I'm Allan Blackman.
And I'm Alison Valance. Mā te wā.